In section 14.1, we're looking at graphs, paths, and circuits. A graph consists of a finite set of points called vertices, or vertex, which is singular, and line segments or curves called edges that start and end at vertices. An edge that starts and ends at the same vertex is called a loop. So in the diagram below, all of our straight lines are going to be our edges. So we have an edge between A and C, we have an edge between A and D, we have an edge between B and D, and we have an edge between B and C. We also have an edge, which is a loop, with C and C because it starts and ends in the same spot. Our vertices are the points that are labeled with a dot. So we have a vertex at A, at D, at B, and C. Be very careful because this middle crossing here is not a vertex. It's just where the two edges are crossing each other. So the vertices will be clearly marked in the graph. So this graph has 4 vertices labeled A, B, C, and D. If there is not more than one edge between 2 vertices, we can use the 2 vertices to refer to that edge. So for example, the edge that connects vertex A to vertex D can be called edge AD or edge DA. The loop can be referred to as edge CC or loop CC. We will always indicate vertices by black dots. Not every point where 2 edges cross is a vertex, and we saw that with that middle crossing. If 2 graphs are equivalent, then they have the same number of vertices connected to each other in the same way. The placement of the vertices and the shapes of the edges are unimportant. So they need to have the exact same vertices and the exact same edges to be equivalent. So let's look at the first graph. Let's label our vertices first. We have A, B, C, and D. And let's label our edges. We have an edge between A and B. We have an edge between B and C. And we have an edge between C and D. Now for the second figure to be equivalent, we need to have the same vertices and the same edges. So let's go ahead and look at the second one. Our vertices on this graph are also A, B, C, and D. And our edges, we have an edge between A and B, between B and C, and between C and D. So because we have the exact same vertices and the exact same edges, we say that these graphs are equivalent. So even though the graphs look completely different shape-wise, they still have the same important information that's needed. Let's look at example number 2. In the early 1700s, the city of, I'm going to butcher this, Konigsberg, Germany, was located on both banks and 2 islands of the Pregel River. The figure below shows that the town sections were connected by 7 bridges. Draw a graph that models the layout of Konigsberg. Use vertices to represent the land masses and edges to represent the bridges. So everybody's graph can look a little bit different, but we need to have the same connections going on. That's the important part. So I'm going to label the right bank as R. That's going to be one of my vertices. I'm going to label the island in the middle as vertex A. I'm going to label the left bank as vertex L, and I'm going to label the other island to the right as Island B. So those are going to be my 4 vertices. I am going to try and place them in a similar placement to where they are on the map. So I'm going to put R at the top. I'm going to put A kind of in the middle. And then I'm going to put L at the bottom. And then put B over towards the right-hand side. This doesn't have to match up perfectly, but I just try to mimic the graph as much as I can. So we've got the vertices because those were the land masses. Now the edges are the bridges. So we see that we have a bridge. We actually have 2 bridges from the right bank to Island A. So I'm going to have one going one way and then the other going the other way. I also have 2 bridges from the left bank to Island A. Let's see what other bridges I have here. I have a bridge from the left bank to Island B. I have a bridge from Island A to Island B. And I have a bridge from the right bank to Island B. So that is what my graph could look like. You could have drew this in a completely different way, but you need to make sure that you have all of the same vertices and the same edges. Let's try another one. Example number 3. The map of New England states are given below. Draw a graph that models which New England states share a common border. Use vertices to represent the states and edges to represent common borders. So our states are going to be our vertices. So again, I'm going to try and place them so that they are in a similar position because this makes it easier to draw the edges. So I'm going to put Maine up at the top. And then below it, I have Vermont and New Hampshire. Below that, I have Massachusetts. And below Massachusetts, I have Connecticut. And I also have Rhode Island. Like I said, your graph may be set up just a little bit different, but you just need to have the same vertices and edges. That's what's important. So let's go ahead and see where our common borders are at. So with Maine, we only have one common border, and that's between Maine and New Hampshire. So we're going to just draw a line between Maine and New Hampshire. Between New Hampshire, we have the main one, but we also have a common border between New Hampshire and Vermont, and New Hampshire and Massachusetts. So I'm going to draw a line between New Hampshire and Vermont, and New Hampshire and Massachusetts. Now let's go ahead and look at Vermont. Vermont has a common border with New Hampshire, but it also has a common border with Massachusetts. So we need to draw a line between Vermont and Massachusetts. And that takes care of Maine, New Hampshire, Vermont. Now let's go ahead and look at Massachusetts. We've already taken care of the Vermont and New Hampshire common border, but we also share a common border between Connecticut and Rhode Island. That takes care of Massachusetts. And now we just want to look at Connecticut and Rhode Island because those actually share a border as well. So we need to make sure we connect a point there. And so that is what your graph should look like when you're done. Let's look at another one. The floor plan of a 4-room house is shown. The rooms are labeled A, B, C, and D. The outside of the house is labeled E. The openings represent doors. Draw a graph that models the connecting relationships in the floor plan. Use vertices to represent the rooms and the outside, and edges to represent the connecting doors. So just like in the previous problems, I'm going to try and put my labels close to where they're at in the original graph. So I have E that's outside here. I've got room A. Room B. I've got room C. And room D. So now the doorways are going to be our new edges. So let's go ahead and see where we have our doorways at. So we have a doorway between A and E. We have a doorway between E and B. We have a doorway between A and E again. So we just need to draw another line. We have a doorway between A and B. We have a doorway between E and C. And another one between E and C. We have a doorway between C and D. We have a doorway between B and D. We have a doorway between A and C. And we have a doorway between D and E. Again, your graph might not look exactly like mine does, but this ends up giving you an idea of what rooms are connected and what rooms are not. The degree of a vertex is the number of edges at that vertex. A vertex with an even number of edges attached to it is an even vertex, and a vertex with an odd number of edges attached to it is an odd vertex. Two vertices in a graph are said to be adjacent vertices if there is at least one edge connecting them. So in the diagram below, vertex A has 5 lines that are coming out of it. We have 1, 2, 3, 4, 5 different edges that come out of it. So that is an odd vertex with degree 5. With B, we have 3 edges. With E, we have 1, 2, and the loop has 2 because it's coming out from both directions. So that ends up having a degree of 4. Vertex D has 2 edges, and so does C. So the biggest thing to remember is that a loop will contribute 2 extra edges. Any vertices that are connected by an edge in this graph would be adjacent. So for example, A and E would be adjacent vertices because there is an edge between them. So for example number 5, we're going to list all the pairs of adjacent vertices for the given graph. So let's look at A first. We have an edge between A and B. We have an edge between A and C, and an edge between A and E. We also have an edge between A and D, and that matches because the degree of the vertex of A is 4. Let's move on to B. Now, if we already have an edge written, we don't have to write it twice. We know that B and A already have an edge, and we took care of that, but the only other edge is BC. So B and C are adjacent vertices. Let's look at C. We already took care of the C and A edge and the C and B, so there's no extra ones we need to consider. Let's look at D. D is only connected to A, and we've already taken care of that. And the last one is E. E is connected to A, and we took care of that, but E is also connected to E. So those are all of the edges that we have in the graph. So that means my pairs of adjacent vertices would be A and B, A and C, A and E, A and D, B and C, and E and E. A path in a graph is a sequence of adjacent vertices and the edges connecting them. Although a vertex can appear on a path more than once, an edge can be part of a path only once. So looking at the graph below, starting at A, we're going from A to B, then we go from B to D, and D to E, which is where it ends at. All of these edges only appear once in the path. A path does not have to include every vertex and every edge of a graph. A circuit is a path that begins and ends at the same vertex. Observe that every circuit is a path, but not every path ends at the same vertex where it starts. So not every path is a circuit. So a circuit is a path, but not every path is a circuit. A circuit is a special kind of path. So looking at the graph below, we're starting at B. We move from B to D, D to F, F to E, and we end back up at where we started at B. A graph is connected if for any two of its vertices there is at least one path connecting them. A graph that is not connected is called disconnected. A disconnected graph is made of pieces that are connected by themselves, called components of the graph. So looking below, you can see the connected graphs have at least one edge between all of the vertices. Whereas in the disconnected graph, we are missing that edge from B to D in diagram C. And also we're missing an edge to connect our two shapes here in diagram D. A cliche says that if you burn a bridge behind you, you'll never get back to where you were. This cliche tells us something about the word bridge in graph theory. A bridge is an edge that, if removed from a connected graph, this would leave behind a disconnected graph. For example, let's compare A and C. That edge, BD, if it was removed, would leave vertex D isolated from the rest of the graph, which would give you what figure C is. So BD would be a bridge. The same thing goes for B and D. That edge between B and E in figure B is a bridge because when I removed it and I got figure D, I have two disconnected graphs.